Hello everyone, thank you all for joining me today. It is January 20th and today I'm going to be solving LeetCode problem 1721, swapping nodes in a linked list. So let's get started. You're given the head of a linked list and an integer k. Return the head of the linked list after swapping the values of the kth node from the beginning and the kth node from the end. The list is one indexed. So in this example, we are given the linked list, and the kth node from the beginning would be the second node from the beginning. And since this is the first node, this is the second node, and we're swapping it with the kth node from the end, which would be this node. These are swapped, and we see we get a resulting linked list of 4, the value 4 being in this node and 2 being in this node. And then we return the head. And then in this example, we are swapping 1, 2, 3, 4, 5, this node with this node with the value 8. The node with the value 7 right here with the node with the value 8. These are swapped, and then we have the resulting modified linked list. So with that in mind, it is possible to even swap a node that is beyond the middle. Like if we said, well, let me see the constraints real quick. The number of the nodes in the list is n. 1 is less than or equal to k, which is less than or equal to n. Okay, so if that's the case and we're swapping, yeah, we can swap any node as long as it's the k is within the range of n. Okay, let me exit out of this because I don't like to be insulted while I'm trying to solve LeetCode. Okay. So k equals 2. So how can I swap these? If I traverse through the linked list, let me copy this over first. If I traverse through the linked list and initially we're at an index of 1 because we're saying this is one indexed, I can keep on iterating through the linked list until the index is equal to the value k, which is 2. Index equals 2 at this point. So we know that this needs to be swapped with an index at the end. But we don't necessarily know how many nodes are in the linked list until we traverse through the entirety of the linked list. So maybe I'll just put a B for beginning. And if we keep traversing, we do have to traverse through to the end because, yeah, k could equal, we don't know which node they're referring to as k equals 2 until we get to the end. Then we can go back a couple steps and realize that that is that node. So I'm kind of thinking this could be an okay idea, but what if we had a dictionary that contained each node where the key is the index of the node starting at 1 and the value is the actual node, meaning this would be the head node, 2 would be the node with the value 2 right here, 3 node, 4, and then 5 is a node, and I'll just mark it as the tail. That's not the actual value. Let me redo that. I'll do this, just so you know which one I'm talking about, although it's a little bit obvious. So we have 5 key value pairs in the dictionary. K equals 2. So then we could get the key value pair with the key 2. And then since the length of the linked list is the length of the dictionary, the length would be 5. And then that tells us that the index we're going to swap is index 2 with index length of, I'll just say length for now, with index length minus k. Okay, that works. So then swapping, I'm only swapping the values. So why don't I just say we have these 2 nodes now, and index 2 with index length minus k, which is the same as index swap node with key 2, I should say, with node with key 3. Is that correct? No, because it's 1 based, so it'd be length minus k plus 1. So it'd be 5 minus 2 plus 1. So it'd be with key 4. And we're just swapping the values. So then, yeah, I think that's fairly simple. If we have the nodes, then we just say node 2.value equals node 4.value, node 4.value equals node 2.value. That can be even written in one line. Okay, so then the time complexity of this is the time it takes to iterate through the linked list. The space complexity is the space of creating a dictionary, which would contain the number of nodes in the linked list. So that's O of n and O of n as well, for both the time and space complexity. Now that's a good solution. It can be reduced though. We can avoid using that space by traversing through the graph again. And then, since we already have the first node that we need to swap with, we can just iterate through the linked list again until we get to the node 4, the length minus k plus 1, and then swap those directly, and then just return the head. So that'll save on space, and that'll reduce the space complexity to O of 1, because we're just creating the variables and we're not needing to create any data structures. And then the time complexity is still O of n. So I'm going to go with that approach. Let me read the problem again and think for a minute about any edge cases that could happen. K is less than or equal to n, which is less than or equal to 10 to the 5th power. Excuse me. Okay, so I'm going to go with that approach of iterating the linked list twice. So we need to know how many nodes are in the linked list. There's guaranteed to be at least the number of nodes in the list is n. So there's guaranteed to be at least one node. Okay, so if we're initially at the head node and then increment by 1, 2, 3, 4, 5, that's 5 nodes. So I can swap, I can store the initial node that we're going to swap with. I mean, I could just do it right here. Like I could say node 1 equals none, and then if length equals to k, node 1 equals to cur 1, 2, node 1 equals to cur. Okay. I'll reinitialize the cur variable to cur equals head. I don't even need to reinitialize that or initialize that. Cur equals head, length plus equals to 1, 1, 2, 3, 4. If length equals to if length equals to k, wait a second, I did something wrong. This will be 5, so I don't need to increment that. Cur.next. So if that's 5, and cur equals to 2, no, it's if length minus k plus 1 equals to 0. Is that right? So 5 minus 2, which is 3, plus 1, 4. I'm getting a little bit hung up here. Five nodes, length is 5. We need to stop when k equals to 2. No, when length equals to k. So we decrement that. Length minus equals to 1. So if k is 5, or no, if length is 5, sorry, we start at the head node. And now its length is 4. Now we're here, 3, 2, 1. And now we need this node. If length minus 1 equals to k, then node 1.val cur.val equals to cur.val node 1.val. And then we can just return the head. And I'll leave this anyways. Okay, let's go back. Length gets incremented all the way to 5. Yes. So 1, 2, 3, 4. Wait, no. 1, 2. Node 1 is set to cur the node. We keep traversing. And we get the total length of 5. We reinitialize while cur this needs to be above. While cur length minus equals to 1. So the length length equals 5. Cur equals to node 1. We enter the loop. Length is 4. Is 4 minus 1, which is 3. Is that equal to 2? No, it's not. Cur goes to the next node, 2. Length minus equals 1. We're back to the next iteration of the loop. Length equals 3. Is length minus 1 is 2 equal to 2? Yes, it is. But we're not at the node we're swapping, so I did that incorrectly. Five plus 5 plus 2, 7 minus 6. I'm doing something really weird with how I just need a way to find if I'm at the second node from the end of the linked list. If there's 5 nodes, I need to get the 4th node. Index, I think it's length minus k plus 1 actually. Minus k plus 1. But what is the condition though? That is when I'll get 4. Length is 5 minus k. I'm having a brain spasm. The length is 5. K is 2. We need to get 2 to the left of the amount of nodes plus 1. If k plus 1 equals to length, and then maybe we can keep on incrementing k. 2, okay, so this is 2, this is that. I think that's right. Strangely, I think this is right. So this would be 3, length is 5. So we're on the initial node, length is 4, length is 3. No, that's not right. Total length is 5. Length is now 4. Length is now 3. Length is now 2. Length is now 1. Five, 4, 3, 2. That's simple then, right? Did my brain just go haywire then? Total length is 5, now it's 4, now it's 3, now it's 2, now it's 1, so then it's length plus 1. Okay, so let's start that over then. Head node, okay, length is 5. We're at node 1. This gets decremented. At node 2, decremented. At node 3, decremented. At node 4, 2 equals to the length. Four, 3, 2, 1. Case 2, 5. So that's 4, 3, 2. Oh, wait a second. Okay, I'm sorry. So this is actually, so this is going to be 6 then. So the condition, let me rewrite the condition. Or let me rewrite the condition in here. So if 2 equals to 6 would be the condition. Okay, so we're at the first node. This gets decremented. This gets moved over to node 2. Now this means if 2 is equal to 5. Okay, this gets subtracted. We move over to node 3. This gets turned into 4. This gets subtracted. We move over to node 4. This turns into 3. So then it's just if k equals to the length. Okay, let's run it. Fair enough. So this did this not even run? It ran 3 times. Let me see if I got the correct value for node 1. Which should be 2. Okay, got 3. It's because of this one index thing kind of messed me up, I think. Now we got 4. If length 1, 2. Oh, I see. So now at least I'm getting 2 from that, which is correct for node value, which is what I want. So we're printing test 3 times. K equals to 2, length equals to 4. Then 3, then 2. So then it'd be length plus 1. Okay, well that's good. Let's see if it runs now. Great. Runtime memory not fantastic. I had problems with the indexing. Let me think about how I can improve this. The space of creating a copy of the node, is that really that big of a deal? Let's see if anything changes if I run it again. No. Yeah, I don't see anything else I could have changed to make it faster. Okay, well, now it's time to compare it to ChatGPT's solution. Yeah, I knew this was slightly awkward second pass logic. That is valid. It's completely valid. It's hard to reason about under pressure. It can be done in one traverse. It can be done in one traversal. Maybe a second traversal, though, right? Two full traversals. Using one pointer to reach the kth node from the start. Then move a second pointer from the head. Oh, that's right. That is the what is it called? It's not Floyd's cycle detection. Is it? Yeah, I've done similar problems or a similar problem to that before. But I never understood what the logic behind it is or the theory. Use one pointer to reach the kth node, then move a second pointer from the head. The second pointer will land on the kth node from the end. Yeah. Okay. No, that's not Floyd's cycle detection then. Excuse me for being a little bit burpy today. I'm drinking Zevia's Vanilla Cola. Get your Zevia today by using promo code Brandon. Okay, can you explain the theory behind... Yeah. Yep. No, okay, it's not... It does use too much of a purpose. Now, I'm probably just going to be doing... I'm going to be reading this and saying interesting a lot, so if you guys don't want to watch this, I totally understand. But this is valuable to read this over. The gap between the first and the second nodes is k minus 1. So once it gets to the end, the second node will be at K. Yes, the distance between the first and the second never changes. That is key. Since the distance between them stays constant, when the front pointer reaches the end, the second pointer must be at the kth node from the end. Fantastic. Okay, well, certainly learned a bit. Thank you all for joining me on this fantastic January 20th. If you're in a different country, maybe it's January 21st. Either way, I hope you're doing amazing. And yeah, I'm really happy that I chose this problem. Really happy you guys joined me. And let's keep moving. Take care, everyone.